Hi, my name is Florian and thank you for joining my presentation about peering automation using OpenConfig. On a side note, and before I get started with the main topic, I'd like to say that Arista Networks is proud to announce that we teamed up with ISOC to become a founding member of the MANRS Equipment Vendor Program. So let's get started, and what is this OpenConfig actually? OpenConfig is an effort to create vendor-neutral data models in Yang and is mainly driven by networks itself. Besides that, OpenConfig is also offering interfaces to communicate with the network devices, to change configuration, and obtain state of the network using streaming telemetry. OpenConfig is still evolving as I speak today, and the Yang models are published on OpenConfig's GitHub repository, the links you see below on the slide. The Yang data models provided by OpenConfig are abstract and therefore vendor neutral. It allows a great level of automation and service provisioning across multiple vendors, as you should be able to use the same OpenConfig input data and let the vendors do the heavy lifting to convert it to their own configuration language. As there's always a but, there are not only OpenConfig's own Yang models, but also vendor-specific ones performing functions which are not yet defined by OpenConfig itself. This means there is an incomplete coverage of functionality if it comes to the abstracted approach, although this is something being addressed and improved over time. So let's give you some more overview about the interfaces OpenConfig defines. First, there is gNMI, the GRPC Network Management Interface, which is used for the most functions I will show you today. gNMI is used to obtain details about the OpenConfig capabilities from the device, get or set configuration, and obtain state data like status of a BGP neighbor or interface. You can also subscribe to certain state data as a constant stream to obtain changes to the state in real time. In addition to that, there's also gNOI, the gRPC Network Operations Interface, which is used to perform system-related tasks like upgrading a device or pinging trace routing in IP. Also here I will give an example later on. As you now understand what OpenConfig is and how we can communicate to the device, let's get back to the real purpose of this presentation. We want to automate peering. What do I need for it? First, I obviously need my own interface details I got from the IXP. In this case, my own IP address on the peering platform. Could automate this as well, but to be honest, I was a bit too lazy to do that. So let's focus a bit more on the dynamic part, obtaining the BGP neighbor details of a peer at a given IXP. PeeringDB is a great source of information for this, so we can leverage their API to get something like the network name, IP addresses, and ASet details. Once I obtain those, I want to make sure I only accept prefixes listed in their ASet. Therefore, I use the information from PeeringDB and let BGPQ4 do its magic to give me the permitted prefixes. Afterwards, we let Python, based on the OpenConfig Yang models, produce the JSON data and push it to the device via gNMI. The script itself for this particular workflow has been uploaded to GitHub, but please note that this is just a proof of concept and not a production-grade piece of code. So let's have a look what kind of OpenConfig capabilities our device supports for BGP. In this example, you can see the implementation of OpenConfig Yang models, as well as some vendor-specific ones. In addition, you can also see the version of the supported model. The vendor-specific Yang models are usually published by the vendors itself. In Arista's case, you will find them on GitHub. Now let's dive a bit into Python. As I mentioned earlier, we want to not only configure the peer, but get started with the interface itself first. So a routed interface needs to have an IP address, which we got assigned from the IXP. In this case, it is defined in the above variable and being used throughout this code snippet. At the end of the script, we write the generated information to a JSON file. And this is how the generated abstracted JSON data actually looks like. As you can see, it doesn't look anywhere close to a regular network device configuration, but all the necessary data is there. All those files are built the same way. You start with the OpenConfig context, and then work down your way to become more and more specific until you actually define the proper items. With gNMI-C, an open source gNMI client, we push the JSON file to the device, and the network device itself then converts it into its own language. We will also be informed if the operation was successful or failed. So to sum it up, the JSON file shown on the previous slide generates the configuration shown on this slide. After we generated and applied the interface configuration, it's time to obtain some peer details from PeeringDB. They're hard-coded for this example just to demonstrate the workflow. As you can see, we call the PeeringDB API using an ASN as a parameter, extract overall peer details like the human-readable name, company name of the peer, as well as the AS set. Then we look for a certain IX ID, which is a unique identifier of an IXP inside PeeringDB. From this particular dataset, we are then extracting the IPv4 and IPv6 neighbor IP. As we configured the interface and obtained the IP details of the peer, let's see if the peer responds to pings. This we can do using gNOI, the operations interface. Even the output of the ping is in JSON and could be used in some kind of further workflow. Good, the peer is reachable. So now it's time to generate the prefix lists and route maps to make sure we don't accept any prefixes not belonging to this ASN or their downstreams. We call BGP-Q4 and tell them to give us its output as JSON. We then generate a new prefix list and add all the prefixes to it. This could also be used to update prefix lists in the future, like automated on a regular basis. The output for the prefix lists in JSON would look like the following. It seems a little bit redundant, but for lists like those, you have so-called multiple key identifiers, which will allow you to specify and identify those particular subcontexts in the future. Yet again, we push it to the device using gNMI and let the device do its magic. The output is the prefix list just as we wanted it. With similar Python code, which is all on the GitHub repository I showed earlier, you also JSONified the route maps. In my case, they're pretty simple. Match on prefix list, then accept, as well as a drop everything at the end. Once we pushed it to the device, we get the pretty route map below. In my example, prefix lists and route maps are part of the same JSON file, and I'll show you later on something more in the demo. Now off to the more interesting part, and let's have a look how the abstracted JSON data of a peer would look like. You can see all the details and references to the previously obtained data from PeeringDB, and in addition to that, we will also apply the route map to the neighbor. It is important to mention that some vendors might have implemented safety measures around referenced objects. In our case, we would fail the update of the configuration if the route map is not existing. As we did everything in the correct order, the route maps are there and the add will succeed. OpenConfig not only offers add and update functions, but also the possibility to delete configuration objects. In this case, we remove the previously generated neighbor from the configuration. As you can see, it is even VRF aware, which can help with the automated deployment of VPN-based customer services as well. If you want to learn more, I can highlight the Arista Open Management documentation as a starting point. It's written by engineers for engineers and contains a lot of valuable information around OpenConfig and how to work with the Yang models. Again, most of the details and explanations on the website are vendor agnostic, but may slightly differ based on the OpenConfig implementation of each vendor. To sum it up, OpenConfig is a mighty framework, not only for configuration, but also for monitoring and data collection. I haven't even touched those points as it would have blown the scope of this presentation by far, but stay tuned for more presentations in the future. Also, it is still under active development, but it is a good starting point, although you may not be able to achieve everything you can do today by vendor-specific methods. In addition of having OpenConfig publish their models, you are still at the mercy of your vendor to actually implement them, as some kind of translator has to be written for the network operating system, the earlier shown capabilities. Having said that, and obviously depending on your network, it might be also worth having a look at your vendor's own Yang models, which unfortunately drives you away from the agnostic approach, at least until it is fully available by OpenConfig itself. So now it's time for some demo. We do have on the left side just a regular shell, and on the right side a switch. So let's have a look. It is a pretty clean repository. So we don't have any JSON files generated yet, but we now call our Python script, which obtains the data from PeeringDB, runs it through BGP-Q4, and outputs the JSON files, which we can see here now. There they are. So let's have a look at the capabilities of the device. This essentially runs the command I've shown earlier in the slides. So I've just made some snapshots here, shortcuts, to make it a bit easier for this presentation. So next step was to configure the interface. We have a look here. No interface, well, the interface is plain, no IP address configured, and now we want to configure this particular interface. We see OpenConfig applies the configuration. We again have a look here, and the IP address is configured. Now we want to run the ping, and we see it's successful to send to received and each sequence. Afterwards, we want to apply the route maps and the prefix list. So we do show run sec route map. Only the outbound route map is configured. Show run sec prefix. No prefix lists configured. We're having a look here at the route map defined in OpenConfig together with the prefixes, the prefix lists. So first of all, the prefix lists up here for v4 and v6 as we got them from BGP-Q4. And then the route map where we accept the prefixes based on the prefix lists. And the last one is a reject. So we're gonna apply this one as well. Update successful. Run sec route map. There we have our route maps now. And there we have our prefix lists. So last but not least, let's have a look at the BGP neighbor. You see nothing's configured under the BGP context as we speak. So let's have a look here on the BGP configuration. So we have two neighbors, one IPv4 neighbor, one IPv6 neighbor. And we're just gonna apply it to this device. Same command again, and we see the two neighbors being configured. Now we also just want to delete the IPv4 neighbor. That's just done like this. So you see the path we're actually deleting. And you see the v4 neighbor is gone, the v6 neighbor is still there. I hope I was able to give you some insight on how to automate your peering based on OpenConfig. And if you have any questions, please feel free to drop me an email at florian@arista.com. Thank you very much for your attention and have a great day.